Alright, hell yeah. So we have a dynamics problem. We're going to do relative motion. So what we have is the relative motion of 2 points. You can kind of read this. This is going to be the definition. What we're going to say is that the velocity of any point on a rigid body is maybe the velocity of a known point plus the velocity of what we're trying to find as seen from that point. Hell yeah, that's confusing as hell. And so I kind of made a short little video to cover that. So definitely, I'll try to link that actually for this one. But let's use that process because I think these are kind of difficult. And this problem I did last night, but I was kept getting the wrong answer. And so I'm going to do this in 2 parts. Like one is like, hey, let's solve it using that equation of relative velocities. And then part 2 will be like, hey, can't we just figure this out from using trigonometry? Now, some of these problems, the trigonometry gets pretty complex of like how to set it up. You know what I mean? Where the prerequisites for that are for sure knowing the derivation of law of cosines, you know, from scratch. For sure, I think that would be like you would definitely want to know that, because if you don't even know that from scratch, then you're just using equations again you're not going to get like the juice. Anyway, so hell yeah. So we have crank AB. That's going to be this thing. It's pivoted at A. It's just going to go around in a circle. You know what I mean? Let's say it just goes around in a circle, and then if this thing is over here, this rod, rams that way. As this thing comes back, it rams that way, you know what I mean? So this rod goes back and forth at D. This point can pivot, you know what I mean? So, because obviously as this thing is down here, that angle is going to be opposite. So if this is all the way down here, hell yeah, you're going to have that bar be the opposite. Alright, so let's read what this wants us to do. It says that this AB does rotate counterclockwise with an angular speed. I'm going to go omega AB, and it's going to be 16 radians per second. So that's going to be 16 radians per second. I'm going to put a K hat on here because with using the right hand rule, we have that's going to be, what's going to be K hat. It's rotating about, if I put some axes on here, and this is going to be really helpful. This is where I kind of ran into my errors. This is going to be the positive X. This is going to be positive y. And then so if this is the x-axis, y-axis, cool. I mean, the z-axis is out of the board, but still this is a 3-dimensional object. These problems are just like planar motion, so we can make them on a 2D surface. Hell yeah. Alright, so what does it ask for? Calculate the angular velocity of bar AB. So, and this is kind of fascinating. I'm going to use this demo because these are 4 lines drawn on a rigid body. This little card is a rigid body. And if I rotate it, what happens to all the lines? Every single line rotates the same amount. You know what I mean? So I've drawn this. So this is about 20 degrees. I'm going to rotate it 20 degrees. And now this goes perfectly horizontal and vertical. And I even have this card to show that if I put this angle right there, this card, is now horizontal and vertical. And if I go back to here, I have this card drawn where, that angle is going to be the same. But yeah, that is very fascinating, where this is one that I need to come back to every time. If I have a rigid body and I draw whatever line on it and I rotate it, that line is going to rotate. You know what I mean? So if this is a rigid body and I have this line and I know that this line rotates like 20 degrees that way, all 4 of these lines rotated 20 degrees that way. Booyah. Alright, so hell yeah. So let's, so what we have is that this bar BE, this bar BE, you know what I mean? If this rotates up like that, it's going to, well, and then what we have is this, omega is a change in angle, change in time. The units on this are radians per second. And I would just even write this as degrees per second. That's an angular speed. I mean, this does not have to just be radians per second. It could be revolutions per second, degrees per second, you know what I mean, or per minute. But it is a change in angle, you know, and a change in time. It's similar to velocity, how velocity is a change in position, change in time. And you can even write, you know what I mean, change in position, change in time, change in x, change in t. This is velocity. All right, hell yeah. And I think that's useful because when we talk about velocity, if you're driving in a car, you might say, hey, I'm driving in a car, but I was at location 1, and then I was at location 2. We talk about that a lot, right? And so same thing with angular velocity. Hey, I'm at this angle right here, right now. This is, you know, angle 1. And then at some other time, I'm at angle 2. Cool. So it looks like you went from angle 1 to angle 2. So that's going to be your change in angle. Just like this is going to be your change in distance. And you know what I mean? Hey, how long did that take you? Well, it took me that long. Well, how long did it take you to change this angle? Well, it took me that long. Cool. And then sometimes, you know what I mean? This is useful because, like, I don't know how fast you were going, how slow you were going, but I do know, hey, I know your average velocity is going to be your change in position, change in time. Hey, I know your average angular velocity is change in angle, change in time. Booyah. For these problems, I mean some of these, we're just going to be talking about constant velocities anyway. So this thing is always moving. You know what I mean? Some sort of motor is powering it, so it's just always rotating at the same speed. It never was stopped. It was just always going. You know what I mean? So if it's kind of similar to driving. You know, the second you hit the interstate, sometimes that's when you clock your time. I'm going to drive, you know, 80 miles an hour from one town to the next town, and that's the distance. That's the speed that I'm traveling. I'm traveling at an average speed. I'm traveling a distance. So I never really accelerated. I didn't go from 0 to whatever. Hell yeah. So that's what we have here. We have constant velocity, constant angular velocity, problems. You know, things are moving with a constant speed. Now, I guess due to geometry, like even this, well, you know what I mean, I can just see that, like, this bar isn't moving at a constant speed. You know what I mean? Because just the way a circle works, like over here, if I move B from there to there, this bar doesn't move at all this direction, hardly at all. Even from here to there, this bar hardly moves, you know, through D. But, like, if I'm at the top of a circle, like right here, you know what I mean? Hell yeah, look at that distance. Like, literally, when this bar moves from here to there, it's literally, D is, this bar is moving through D that much. Hell yeah. Alright, cool. But these are a type of dynamics problem where they just ask for, like, hey, something at a point. Like, hey, at this time or this angle, what's happening? You know, so that's what it says. Calculate the angular velocity of bar BE when this angle is 60. So when this angle is 60 degrees, I want to know what the velocity is. Because we just said that, hey, if this bar was over here, the velocity would probably be 0. You know what I mean? And then when it gets up to some sort of tangential, now we do have an angle that develops, so, but I think it would be 90 degrees. Doesn't have to be. Well, I don't know. Yeah, there's going to be some point where this is going to be traveling the fastest. And hell yeah. And that's fairly interesting because I'm actually going to do this. This is actually some of the harder things to do, to be like, can I guess? Because I got this here's the answer. Cool, here's the answer in the back of the book. And I got it wrong like 3 times in a row. But that's going to be for part 2. Part 2, I used trigonometry to get the answer right. And then I came back and figured out all my mistakes. Because we're going to use those angular velocity equations, and it's using the cross product. And I don't know, I think there is just a huge place, a lot of places to make mistakes. Cool. But let's get a sense of this. 16 radians per second. Alright, so I'm just going to say to myself is like I need to always think of radians as groups of 6. That if I have 6 of them, that's going to be one full rotation of a circle. So for some of these fast spinning problems, this thing, let's say 16 divided by 6, well 18 divided by 6 is 3. This thing's spinning like 3 times. Cool. You know what I mean? And 6 times 4 is 24. Yeah, so 6 times 3 is 18. 6 times 2 is 12. You know what I mean? So hey, this thing's spinning between 2 to 3 times per second. Alright, so good to know. And hell yeah. And what do we know about angular speed and, you know, if I know something, well, it's this concept of radians. Like, what is a radian? So a radian, this is really good to do, is if I have this as my radius, a radian is an angle, but it's like if I take the radius and cut a string and then drape it around the circle, I'll probably get to about there, right? You know what I mean? This length, this radius, if I measured it and cut a string, draped it to there, I would get to there. So that's going to be the angle that I would get. It's approximately 60 degrees. It's like 57.3 or 4, who cares? You know what I mean? It's less than 60 because if I divvy up a circle into, well, because I'm gonna get to there. I'm gonna have 1, 2, 3, 4, 5, 6, but then I have 6.28. You know what I mean? It's 2 pi. Pi is 3.14. Double that. That's where you get the 6.28. You know what I mean? You can see that visually. All right, so we just talked about how, you know, angular speed is a change in angle per time. So let's get, what is this? So we're gonna say this is 1 radian. So let's write that out. 1 radian, and that distance is the distance that we traveled was 1 radius. So if I move an angle of a circle through an arc of 1 radian, and I'm at the perimeter of the circle, you know what I mean? I'm going to move a distance of 1 radius. Cool. Now, I could be anywhere on the circle. I could be at the halfway point. Cool. I'm going to move a distance of half the radius because it's linear. You know, that is something not to mess up. Is the relationship between a radius and a circumference. Radius is proportional to circumference, and it's linearly proportional. You know what I mean? It's just a proportional constant that's related. Diameter is proportional to circumference. Double the diameter, you double the circumference, because it's just proportional with a constant. What's that constant? Probably pi in that case, 2 pi in that case. Hell yeah. Alright, but yeah, so that's really good to do. Draw a circle, draw the radius, figure out what 1 radian is. Because we're going to have, like let's say this thing was moving 1 radian a second. You know what I mean? Let's say this bar is down here, and it's going to be moving at a speed of 1 radian in a second. How far did we travel? Well, this is the radius, and we traveled 1 radian, so we traveled 9 inches if we traveled 1 radian per second. And then, what would be our velocity? Our velocity would be the distance that we traveled. We traveled the length of that arc, which was 9 inches. So that's going to be, we traveled a distance of 9 inches in 1 second. So our velocity, and that's velocity tangential, would be 9 inches per second. Now this brings up the equation that I just don't think, I graduated without knowing this equation, is that radians, this angle in radians times radius is arc length. You know what I mean? This equation, I mean, I just verbally say it and put it in this. I'm going to say radians times radius is arc length. Whoops, arch length. Hell yeah. Because I'm going to say radians times radius is something normal. So this is kind of my little saying. Because there's going to be 3 equations that use radians. We have radians, and then we have radians per second, and then we have radians per second squared. So this is going to be angular speed times radius is, what would that be? That's going to be tangential velocity. And then this is alpha, which is change in omega, change in time. This was change in angle, change in time. And then this was just the angle. The angle times the radius. This is going to be the, that times the radius. But we get something normal. This is going to be tangential acceleration. Hell yeah. Alright. So this just one equation is very useful, and then we can kind of get a quick answer. Because, I don't know, like, especially when things are moving at a constant speed. If it's not moving at a constant speed, if that speed is fluctuating, you know what I mean, then you know what I mean, if at point 0, at time 0, hey, I might not have any speed at all. And then at time 1, I might have like 10 meters per second if something's falling. And so that's a huge difference in there. And and then I need to figure out if that speed is linear or not. And so one way to do that is like, hey, if I want to know what the velocity is at t is equal to 0.5 seconds, well, if I have an equation on here, maybe I would take the velocity at t is equal to 0.49 seconds, and the velocity at t is equal to 0.51 seconds. And then I would have, hell yeah, what are we doing? Oh, my bad. For this, sometimes you would have like the distance. So I would want the distance at that time, and then the distance traveled at that time, and I would have a change in distance, and then I would know my change in time was just like 0.02 seconds. You know what I mean? So I have a very small change in distance, but I have a, relative change in time, and then so I could figure out the velocity at that point. Following things is just linear. You know what I mean? Hell yeah, where are we at? So yeah, we're going to try to guesstimate this. So our angular speed is constant, 16 radians per second. If it was 1 radians per second, I would be going 9 inches per second. If I'm going 16 radians per second, I'd be going 9 times 16 inches per second. So that's how fast we're going. That's how fast this point is moving. Cool. That's just this point right here. And, you know what I mean, we're just doing this from kind of an intuition perspective. Because, I mean, you would already need to know this aspect before doing this problem, being like, hell yeah. Excuse me. I know what the tangential velocity of B is. That's omega, you know what I mean, times the radius. And then radians times radius, what is that? That's tangential velocity. And we're gonna look at this as a vector crossed with a distance vector, and we're gonna have to get these in the right order. It's omega cross r. It is not r cross omega. You know what I mean? And then we're gonna figure out why it's omega cross r using the right hand rule. So we're gonna do that. Hell yeah. But right now we're just kind of getting just a general gist of what's happening with this problem. And so 9 times 16, I'm going to try not to use calculators. That's 10 times 16, that's 160 minus 9. Hell yeah, that's 151. Is it? Doesn't seem like it. But 10 times 16 is 160, minus 9 is 151. Holy hell. Doesn't seem like it. You know what I mean? But, I mean, we could do it like this now. I hate doing this. 9. See, it doesn't seem like it. How do we mess that up? 9 times 16. Yeah. I'm glad my spidey sense. It's 9 times 16. And then minus 16. So, hell yeah, it would be 150, but minus 6, 140, 144. Hell yeah, 9 times 16, we should have got there a little bit easier, too, if that was just 144. How could we have done this easier? I don't know. You know what I mean? It's 18 times 8. That doesn't help. I half that, doubled that. That really doesn't help. Booyah. But I could say it's 3 times 6 times 16, and then boost this up to 12, 8. Nah, this one sucked. But anyway, is it 144? Hell yeah. 9 times 6 is 54, 9 times 9 is 9, and then we got 14. I'm glad I didn't mess that one up. Alright, hell yeah. So we got 144 inches per second. That's going to be the speed. Cool. And, oh, that's interesting. That's not even what the problem asks at all. It just asks what this the radial speed of this is. But we're doing it anyway. All right, hell yeah. So we're back, and booyah. Let's grab a new sheet of paper. Yeah, we're just trying to get some ideas of what's going on here. So we have an angular velocity of 16 radians per second. We have a radius of 9 inches, 9 times 16, so we have a tangential velocity of 144 inches per second. Cool. And what are we at? Yeah, cool. So we got that aspect. This thing's going to be at 60 degrees. We said if it was here, that's really not driving this thing at all. We said that if this, at some point, this tangential velocity, if it moves, this tangential velocity is going to be the same. Because if this moves in 1 second, let's say it moves from here to there, this thing is also going to move from here to there. So I would say the velocity is going to be very similar. So, but I would say the velocity at D is going to be less because, you know what I mean, we have, it's not directly in line. The only way the velocity would be perfectly, if this tangential velocity was directed straight down this rod, hell yeah, then it would. So I'm just going to guess 130. 130 inches per second. Maybe 120. And then we can maybe double check that. This problem doesn't ask for it. It doesn't ask for the velocity at D, but that's something that you can solve for. Alright, what it does ask for is what this angle change is going to be. D is kind of a pivot here, so this is a pretty easy one to solve from a trigonometry perspective. So let's say at 60 degrees, this is where AB is. And in 1 second, this goes from here to here. You know what I mean? And so we have something that had an angle like this. And now 1 second later, this thing's at the top of its arc. And now we have something that has an angle like that. You know what I mean? Let's just postulate that that's what happens. And cool. So it took 1 second to go from there to there. What angle do we have? You know what I mean? Sometimes it is useful just to kind of guesstimate angles by doing this. Drawing like a 45. Sometimes I do a thirds first. Do your thirds. And then do the 45. So this is 15 degrees right there. And this angle, let's see, looks less than 15. Maybe it's 10 degrees. Cool. So let's say it does move from here to there. it moves 30 degrees a second, so that would be 30 degrees per second. This angle is going to change by 10 degrees per second. Okay, and even like right here, it's like, whoa, I didn't even know that I could just do a proportional relationship, and that would be fairly accurate. I can say, hey, if this moves, 30 degrees, this one's going to move 10 degrees. Okay, so I can say that if, so this is going to be 1/3, just a quick guess. So I'm already in the guessing realm that if I said this was 16 radians per second, which is, damn it, it's not divisible. I'm just going to turn it to 15. So I have 15 divided by 3. So right now I should say, hey, this is approximate radians of 5 radians per second. And I've not done this. Like, this was brand new. This guessing that I'm doing right now is brand new. I have not done this. And we can see that the actual answer is 4.57. So I learned two things from, this is one is just that I could have guessed. I think it's very difficult to break this down. This thing's spinning 3 times per second. I'm just going to be like, nah, I'm just going to say it takes 1 second to get to there. And then it was just really fascinating that we found out that all we were looking for is a proportional relationship between this change in angle and that change in angle. And so that was pretty sweet. And this is kind of like using calculus in a way. People are just like, hey, can you do some more calculus videos and stuff like that? Well, I'm changing something just by a little bit. If I change this, if I said, hey, I'm going to move this 180, cool. Now my angle, this changed quite a bit, and so, and then what? But if I changed this just a little bit, I went up to 60 to 90. This changed by 30 degrees. This one changed by 10. And now I can see that relationship. So that was pretty sweet. Okay, hell yeah. So now let's try to do this, just smoke it out, and get the hell done with this video. Alright, hell yeah. Let's do this. Okay, so the equations that we're going to use is that I want to know the velocity of B. Well, it's kind of interesting. I just kind of use the relative velocity equations. So the relative velocity equations say the velocity at B is going to be the velocity at A plus the velocity of B as seen from A. So, you know what I mean? If we get SpongeBob, where's SpongeBob? So, and what we're saying is that SpongeBob is at point A, but not rotating. So SpongeBob is going to go to point A, just kind of pick a location, but is not going to rotate. So as this rotates around, what SpongeBob is going to see is that SpongeBob is going to see this rotation, this tangential velocity at B. That's all SpongeBob is going to notice. And that's the relative part. Because maybe A is moving. In this case, A is not moving. So there you go. And what SpongeBob sees is just the tangential velocity at B. And if we knew the tangential velocity, we would just use it. But we don't know it, but we do know that this thing is rotating with an angular speed of omega AB. And so we use the equation. And these are all vectors. I'm going to use vector form. So I can say that velocity at B is the velocity at A plus, and then what is this? The velocity at B as seen from A. SpongeBob is just going to see tangential velocity, which is omega, as a vector, omega cross R. Hell yeah. And then that distance, and this omega is going to be of this rigid body AB. And that distance is going to be A to B. So we're going to say the distance is going to be the distance to B as seen from A. So if I'm at A, SpongeBob, hey, what's the distance to B? Booyah. That's going to be that. That's how you read this. It's going to be A to B. What I think of things, you ever see just in like text, you have like a parentheses, and sometimes, you have a word and then a parentheses. And sometimes the parentheses means to be like, hey, like put that out front. Are you kidding me? These pens cost so much, and it's already done. That's crazy. Maybe I've been going pretty hard, though. Alright, hell yeah. That's the same thing I think of as this sign right there. I kind of think of it in that parentheses. You know what I mean? I don't read this as B to A. I read it as the opposite. I'm going to say, you know what I mean? Like, hey, yeah, that's in parentheses. I don't know if that's a good way to... That's just how my mind's working currently. And so I'm just going to say, hey, this is A to B. A to B. You could have a vector BA, which is B to A. You know what I mean? So if you have this, where you don't have a slash, this is B to A. Cool. Like vector O to A. Origin to A. Hell yeah. You know, that would be the same thing as OA. The vector OA. This would be the same thing as BA. But what we have here is, this would be RAB. There you go. Or just, you know, vector AB. That's from A to B. That's how you, and that's just the relative distance, you know, as seen from A. Distance is just going to be the actual distance. The relative velocity, again, it's going to be non-rotating, and so you're just going to see angular speed. So this is what we're doing right here. Hell yeah. Okay, so we have this equation. And so I'm going to write it out, velocity at B. Velocity at A is 0. And then what's this omega A cross the distance from A to B? Well, let's do that. So we have omega AB is 16 radians. So it's 16 k hat because it's in the right-hand rule. Thumb is up. That's going to be the positive k direction. And we have planar motion. This is the xy coordinate. Hell yeah. And then we're going to cross it with the distance from A to B. Cool. And then so we have an angle of 60 degrees here. So if I go from A to B, I'm going to go in the x direction, and then I'm going to go in the y direction. So we have two coordinate directions. Hell yeah. And then so if this is the angle, I'm just going to put some sun-shining rays. This is going to be the sine component, and then that means that this is the cosine component. When you think of sines and cosines, think of them as percentages of the hypotenuse. Hypotenuse is always the larger number. That means that these percentages are always going to be usually smaller. You know, if you do have a right triangle, hell yeah, there are going to be smaller. Unless you just have like a totally vertical or a horizontal line, you know what I mean? Then one of these is going to be 100%, the other is going to be 0%. But if you do have a triangle, these are always going to be smaller. So how much of this 9 inches is in this direction? And again, the first time around, these percentages do not add up to 100. If I take these percentages and square them, then add them, hell yeah, they add up to 100. Small number, yeah. So anyway, and then because of that, you know, you could have something that's 80% in one direction, and then, you know, close to 50% in the other direction. Isn't that wild? Because 0.5 squared is 0.25, and 0.8 squared, well, that's 8 squared is 64. That's going to be, you know, 0.64. And 0.64 plus 0.25, we're actually under. This has to be 0.866. 0.866. You know what I mean? And definitely 50% plus 86.6% don't add up to 100. But this is one way you can kind of keep visual on things, because, you know what I mean, what is this distance? What I like to do is just divvy up the hypotenuse in half, and then be like, hey, is one of these half? Hell yeah, it is. This is about 4.5 inches, and this is about the whole thing, but maybe 8, you know what I mean? So that's just a rough guesstimate. I could say, and we're going to go in the positive direction. So I could say positive 4.5 in the I hat plus 8 in the j hat. If I was just guessing, but we're gonna do this as we should. This is the cosine component, so we have 9 cosine I'll just put theta for now. It's 60 degrees, as the problem says. But 9 cosine theta in the I hat direction. And plus, we have 9 sine theta j hat. So we're going to do this cross product. Anytime you do the cross product, I do this, ijk. And then just write it again, ijk. That's helpful. The other thing is helpful is to do some sort of coordinate axis. I'm going to do x, y, z. You know, you could do this however you want. You could also do a coordinate axis as, you could do x, y, z. I mean, you could do it 3 different ways. There's going to be 3 different ways to draw this coordinate axis. If, you know, these are going to be your positive, well, there's 6 different ways if you actually drew, you know, any of these into the board, or a plethora of ways to do it. But, I mean, hell yeah. You could also have the x up top. You know, I mean, and how do you do this? If I have the x up top, how do I get these to be, where does the y and z go? Well, if I do want these to be, you know what I mean, the positive directions, and into the board and down to be the negative directions. So if I'm for sure setting those to be the negative directions, I'm going to take my hand, and this is where the right hand rule, like, do I stick my thumb in it or do I use my fingers? If I'm going to start, the starting position is always going to be like, you know what I mean, like kind of like a karate chop, maybe like fingers in X, and then I'm going to sweep them. And then, so that's how I do it. You know, fingers in X, and I'm going to sweep them into Y, and then my thumb is going to be pointing in the Z direction. So thumb and Z, fingers swept into Y. So there you go. Same thing on these. Fingers in the X, sweep it into Y. My thumb is in the Z direction. My thumb should be in the Z direction. If I put my fingers in the X, sweep it into Y. So hell yeah. And then from this perspective, if I cross in this direction, I'm always going to be positive going that way. If I'm crossing this direction, it's always going to be a negative. You know, so if I have I cross J, that's positive. J cross K is positive. But I can't go, if I have I cross J, I can't go I cross K with this little chart. If I go I cross K, I got to go here to I, and then go backwards to K. You know what I mean? So that's why I do this twice. You know, it wraps around. I mean, you could do I, J, K in a circle, and say this direction is going to be positive, this direction is going to be negative. That's a new one to me. I've never done that before. But if I have I cross J is positive, if I have J cross I, negative. K cross J is negative. But interestingly, K cross I, because it kind of loops back around, K cross I is positive. And then on here, what the hell does that even mean? If I have K direction, fingers in K, cross into the X direction, that's I, then I'm going to be positive J. See how K cross I is positive J? Let's pick a negative one. A negative one would be going this direction or just this direction. So pick any of them. How about J cross I? Fingers in J, and I'm going to cross it into I. So I'm going to actually have to shove my fingers that way and sweep. You're always going to be sweeping with the palm this way. You're never going to be like back sweeping. So to actually get my fingers in Y and then sweep them into J, my thumb's going to be down in the negative Z direction, negative K hat. Cool. And, I mean, this is I hat, this is J hat, this is K hat. I like to visually see them as X, Y, Z, but you could also just do I hat, J hat, K hat. Alright, and this is where it gets me confused. I just thought these were cardinal directions, but no, these are actually little vectors with a magnitude of 1 in the X direction, Y direction, and Z direction. That is what the hell got me confused. I graduated without knowing that. I just thought this I hat, J hat, K hat was just like different cardinal directions. No, it actually represents a vector in that direction. So see how we are representing this distance? You know what I mean? We said it's like 4.5. Well, cool. I'm going to say it's 4.5. Alright, I think the best way to think about it is 4.5, but 4.5 is just a magnitude. I need to say that it's in the x direction. And so what I do is I could say, you know, maybe it's 4.5, you know, with the arrow on it with an x direction written right there. But what we have is this simplification of like, hey, what if this was 1? You know, let's say this length was 1. I'm going to have 1 maybe with an arrow, and then I'm going to write the x direction. All we're doing is just, you know, like having just a simple way to represent this. And I'm going to say, hey, a vector in that direction that has a magnitude of 1 is, we could put a 1, we could do a 1 I hat. But the 1 is redundant, and so we're literally, if you see this I hat, this represents a vector of 1 that's, you know, magnitude of 1. Even though we don't write 1 I hat, you know, or 1 I hat like this. We should. So if I actually rewrote this, it should be 9 cosine theta, this is the scalar part, times 1 I hat. This is the vector part. And yeah, just as this vector, I could multiply it by 2, and now it's you know, it's just 2 I hat. It used to be 1 I hat, and now it's 2 I hat. Yeah, and I get how this is hella confusing because it's like you're reducing something to something that's very simple, where you're just like, okay, I have a vector and a magnitude of 1, and in here I still have a, you know, something that's 4.5 in the x direction, and so, you know, why can't I just call it 4.5 hat? You know what I mean? Just make a vector 4.5, you know, and then you know, hat x. I would have to have something that designates the x direction, but all, you know what I mean? So yeah, having something that's 4.5 in the x direction, that is still a vector. I'm having a quantity, and I'm giving you information about its direction. So we're just saying that, yeah, and that's the difference between saying the x direction is it's fascinating. And why didn't they just use x hat? You know what I mean? And y hat and z hat baffles me. But hell yeah, we use IJK, and you get used to those. All right, booyah. All right, so let's do this. Let's do this. So we're gonna cross k and I, and then even this. How do you do this? Well, it's two scalars. You know what I mean? You're still multiplying. Dot product and cross product are still a multiplication. So I'm still taking 16, and then I'm multiplying it by 9 cosine theta. And then I'm multiplying, you know, well, you got to be careful, because these are, how do you multiply vectors? You know what I mean? Because I don't just have, like, you know, a quantity of something, and then I want to double it. Cool, I can visualize that. I have something going this way, and then I want to multiply it by something going that way. I have two vectors that are getting multiplied. And so, I don't think I want to, yeah, I think there's something at a loss. I've been taking linear algebra. But, yeah, like, yeah, vectors don't multiply, you know, super well. But you can get physical properties out of them that make sense. And what we have is, like, if the cross product is always where, like, two things are going to be 90. So if you're torquing if you have a torque wrench, you know, on your car, hell yeah, I'm going to put a force there and I put a force there, and we have some sort of distance between, and I have a torque of FD. Cool. But if I choose to put a force this way and a force that way, I have 0 torque. Torque is 0. If I choose to do some sort of bad angle, let's say 60 degrees. I'm 60 degrees that way, like this is 60 degrees, and this is a horrible angle, is 60 degrees that way. Cool, I just halved my torque. The torque is going to be 1/2 FD. And so what we have here, the torque is a cross product. Torque is cross product of R cross F. And it's in that order. And it's only the component that's perpendicular to the distance of the thing that you're trying to torque. Only the perpendicular component, which is only half in that case, actually drives. And then the cross product from a vector multiplication as a cross product picks up that, with this idea that if two vectors are perpendicular to each other, which the k and I directions are, so if I do have something in the k direction and something in the I, look at that, that's perpendicular, then that plays. I can multiply this straight up, and I'm going to get that as if this was torquing a wrench, a bolt on a car. If the force is in the perpendicular direction to that torque wrench, you're going to get it all. Cool. So yeah, I mean, a lot of people just go for it, but hell yeah, you're still going to have k cross I. You're going to have the scalars multiply, but we still have to do the cross product of k cross I. What is that? I'm going to have still a magnitude of 1. Both have, so there's still a scalar component on both of those. And then we have the vector component. I'm going to do k crossed into I. And then in this case, I'm going to say I have a torque, or some sort of property in the j hat direction. So this term becomes a j hat. And, from here, this is the positive direction. J cross I is a positive. And positive what? It's positive j. So we have a positive j. Cool. And we're going to get a negative, because if on the k cross j in a moment, k cross j is going the negative direction, and that's going to be negative. But hell yeah. So this term right here, these two multiply, and we're going to get 16/9 cosine theta j hat. This is velocity b. Doing the cross product here, your 16 and your 9 sine theta multiply, and then we're going to get k cross j. That's these two. So the scalar component, it's kind of like putting it outside the integral. A lot of things are like that. Where your scalar components can go outside of the vector, operation. And so, and what are we doing for vectors? We're taking the angular speed and then crossing it with the distance. And so even though the angular speed is like, this, it's still a vector, and its vector is out of the page. So I'm going to throw my fingers out of the page in that k direction, and then I'm going to sweep my fingers into the direction of this r. This radius, this r, this radius of A to B, of B as seen from A. And when I do that, then my thumb is going to be in the direction of the property. So we have radians per second crossed with a distance. That's going to be tangential velocity. So that's where my thumb is in the right hand. Well, that's going to be the tangential velocity. Hell yeah. And because k is straight up, and then the r is that direction, then I'm going to get... And if I do k straight up and r that way, I'm going to get all of that tangential velocity. Well, we're doing it as piecewise, where we're going the angular speed crossed with, that direction. We're going to get some sort of velocity of b that way, and then I'm going to go angular speed and then crossed with this distance, and we're going to get some sort of component that way. Those two components add, and they're going to be perfectly tangential at b. Alright, hell yeah. And then we have k cross j is going to be, even on here, I can go k cross j is going to be in the negative I direction. So this is going to be negative I hat. Hell yeah. So I'm going to have minus 16 times 9 sine theta I hat. Alright, hell yeah. So now we're just going to kind of bust this out, I think, because I am about done. Alright, hell yeah. And sorry to do kind of the complicated stuff, probably, you know, just try to brush through it. But now we can use this equation anywhere. This equation works for any rigid body. That's the other thing. Is I'm going to put this rigid body in quotes. We took this rigid body, you know what I mean? Like this rigid body right here. I'm going to call it rigid body 1, rigid body 2. You know what I mean? And that's what we're going to be doing. I can say that, I mean, this could be a rigid body, maybe. It's rotating but not moving. That'd be kind of fascinating. We could actually do that. That is interesting. But yeah, those are the rigid bodies we have. I have a chunk of material there, a chunk of material there, and this slider is a chunk of material. Cool. Maybe we'll try to get more, you know, detailed into that. We'll see. Oh, that is fascinating. Okay, yeah, we'll see what we want to do. But yeah, we're going to use this, you know, this relative velocity equation again. And so, yeah, I mean, it's kind of fascinating. Like, where is point D? Is point D the actual collar? Because that is not moving. You know, the collar is not moving, it's just rotating. That's why it's kind of interesting to actually put this as a rigid body. These are the questions that are just like, I don't want to figure that out. You know what I mean? And so, I don't know. I just said that point D was a point on this bar inside the collar. But I don't know. It doesn't really matter anyway. We could do the velocity of point E over here. So let's try to do that one. I'm going to say the velocity of point E is equal to the velocity of B plus the velocity of point E as seen from B. And what we're going to get is we already have the velocity of B. Oh, and this is kind of interesting because that's the crap thing about this problem is that because of this collar kind of dictates the direction the velocity can be in. So I don't know the magnitude of velocity E. So I'm going to say, so we have velocity E, and we have some sort of magnitude. And then I just don't know its direction. But I do know its direction has to be at this angle. So whatever angle this is, and I'm going to call this beta. And then so I'm going to go over here onto, this is where trigonometry comes in. Do I know this angle beta as a function of theta? You know what I mean? So that's what we're going to do. And even just right there, like that stuff's hard. You'll be like, well, I just want to know what beta is. Well, you can. And for this problem, because we're choosing theta to be 60, but this is a good challenge. Because, yeah, just choose theta to be 60, and then you just have a trigonometry problem. Alright, hell yeah. But if you choose theta to be any sort of angle, then you have betas in terms of theta. And then so I want to know this angle. And so if I do have a right triangle, if I know two things about this right triangle, I know everything about it, which would include the angle. So let's try to figure out two things about this right triangle. I know this is 18, and I know this because this is just 9 cosine theta. And I know this length. This is 9 sine theta. So I know two things about this triangle. I know everything about it. That's kind of do you say the word moniker? I have no idea. But anyway, you know, just phrase or saying. And hell yeah, so we can figure out what B of theta is. I know two things, and I know the tangential things. So then I know that I could say tangent of beta. This is just beta. Tangent of beta is opposite over adjacent. And I know those. Or I could say beta is equal to the inverse tangent of opposite over adjacent. So sometimes it's worthwhile just to kind of, figure out what you do know about triangles. Be like, oh, I do know tangent of an angle is that, and then write that, and then rearrange it. Or just kind of know that, hell yeah, this is going to be the inverse tangent of opposite. You know what I mean? For any of the tangents, inverse tangents, sines, inverse sines, cosine, inverse sines, inverse cosines, the ratio doesn't flip-flop. It doesn't change. You know what I mean? If you're doing inverse tangent, it's always going to be opposite over adjacent. It's not going to be weird and be opposite over hypotenuse. You know what I mean? So it's just like, sometimes those are the quick skills to have in your head. But so we have inverse tangent is going to be the opposite. 9 sine theta divided by, this is going to be 18 plus 9 cosine theta. Cool. Alright, so now we have beta as a function of theta. And why is it a function of theta? Because I see theta twice in there, and then just normal numbers. But if I input a theta, I'm going to get a beta. Alright, hell yeah. And then so I'm just going to assume, sometimes you have to assume things. I'm going to assume that this bar has an omega BE, and I'm just going to assume that it's in this direction. You know what I mean? That it's going to be positive k hat. And if that's the case, I mean, it's just interesting to be like, hey, if this is going this way, hey, this is going to have that velocity in that direction. Which, if I'm setting this to be positive x and positive y, it's going to be negative x and it's going to be negative y. And it's going to be in this direction. And so, that's where sines and cosines. So if I say this angle is beta here, this angle is also beta, you make your hypotenuse of 1, you know what I mean? I hate the unit triangle. I just wish you could do everything without it. Just because I swear it's just like people quit math because the unit triangle. Anyway, hell yeah. And, oh man, I need to get some more ice water, I think. Alright, hell yeah, we're back. Cool, so this component, if this is 1, you know what I mean? I'm going to multiply it by a vector, but this is just kind of the directions. So we're going to have, this is going to be negative cosine beta, and this is going to be negative sine beta. Those are our directions. So I have whatever velocity of E is, multiplied by negative cosine beta I hat minus sine beta j hat. Okay, so that's the velocity at E. I know the velocity at B. I'm going to write that in later. But this part, this velocity of E as seen from B. And it probably would have been better if I said velocity of B as seen from... You could have done that. You could rearrange this equation and say, hey, what's velocity of B? Velocity of B is velocity of E plus velocity of B as seen from E. You know what I mean? So, hell yeah. And I don't know, is there a way to not mess that up? This equation says I want to know this velocity. And that point is going to be on this rigid body. Here's another point on the rigid body that I know, maybe. And then so this point, the velocity of this point is going to be the velocity of this point. Plus, break out my SpongeBob, I'm going to get to that point but not rotate. And as this thing is rotating, what am I going to see? I'm going to see that move tangentially. And that's going to be the velocity of B as seen from E. So it's from here to there. But velocity of B as seen from E. So E to B, that's what I'm going to be looking at. Hell yeah. We'll do this though. So this term right here is going to be omega BE. The angular speed of that bar crossed with, and it's just EB. Hell yeah. And the proof on this is if you have like velocity of the position of B is the position of A plus the relative position B as seen from A. And so if I have position to B, and then here's position. I don't want to get into this. I'm sorry, but anyway, you do a time derivative of that, and it gives you this equation. I don't know how to draw it. I apologize. Anyway, all right, let's do this, and then so I'm just going to assume that this is going to be a k hat. If this turns out to be a negative quantity, I know it was the opposite way. But hell yeah. All right, and then the position from E to B. Oh, and see, yeah, that's where, so dumb. You know what I mean? I'm sorry I changed it. We're just going to change this to D because we know where D is on this. Booyah. So this should have been D the entire time. I'm choosing point D. It's a point on the bar inside that couple. Sorry I chose E. That was stupid. My bad. But it's still omega bar BE. We can still say it's the angular speed of bar BE. But we're choosing point D as our point. And that point is, having that angle. As this thing, the whole bar has that angle. The angle of that couple is the same as the angle of the whole bar. So this term applies for the direction of that whole bar, and it's going to be negative down and over. Alright, brutal. So we have B to D. So this is where we actually get the, our position vector. We're going to go in the negative and then negative direction. So I'm going to have negative 18 plus 9 cosine theta, I hat minus 9 sine theta j hat. Alright, and when we do the cross product, k cross I is going to be that positive direction, but we would be aware of this negative. K cross I is going to be a positive j, but we do have that negative. K cross j is the opposite direction, because it goes ijk, but k cross j is negative. It's going to be negative I. So we do have that. We have a negative and negative is going to be positive. So cool. So that, well, let's just write it all at once. So we have this. We have velocity of B is going to be, well, I don't want to write this more than I need to. So we have this equation is that. Velocity of B is that. And this, we can write this. So this is going to be negative 18 plus 9 cosine theta omega BE j hat plus 9 sine theta omega BE I hat. And this is where I made mistakes of being like, hey, this is going to be negative. Negative and a negative is a positive. This is going to be a positive when we do the cross product of K and I, I'm sorry. It's going to be a positive j hat, but we do have that negative. Alright, so now we're set. So now what we do is we can take the x direction components, just the I components, and so in this equation I have VD, negative VD cosine beta is equal to the I component here, negative 16 9 sine theta. Theta is going to be 60, but beta is also going to be this where we input 60. We haven't done that either yet. And then we have an I component here, so we have 9 sine theta WBE. And it's just interesting, you know what I mean? I probably spend, well, no, I'm happy with the way I do my videos, but I'm definitely getting, oh, this sucks, getting tired. So anyway, hell yeah. So we're going to have the J component, so we have negative VD sine beta is equal to, with the J component there, 16 9 cosine theta. And this is where you make mistakes, and hopefully I do. You know what I mean? Because it's also a skill to be sloppy as hell and see if you can not make mistakes. I'm just kind of curious about that as well. Hell yeah. Okay, so beta is just going to be a constant. You know what I mean? I'm going to throw that in. Okay, cool. VD I do not know. And then omega BE I do not know. Theta is going to be 60. And so the way I did this in my calculator is kind of interesting. So hopefully we can just crank this out. What I'm going to do is I'm going to, like, I'm going to say this is my y term, and this is my y term, and then this is my x term and x term. Now I can do some things off the bat. Inverse tangent of 9 sine 60. And then this is where I make mistakes. So might as well go 9 sine 60. That looks good. And then go 18 plus 9 cosine 60. That looks good. And then take this divided by that. Hell yeah, made no mistakes. Inverse tangent of that. And I'm going to store that as theta. Well, I'm going to store that as beta, alpha b. Sweet. And then, because this is something and times the y term, I'm going to go 9 sine 60. I'm just going to store that as, h. Hell yeah. So this term right here, I'm going to store as h in my calculator. Now I'm going to come to this term, and I'm going to take the negative. So, alright, hell yeah. So last battery, and booyah. And I'm just going to show you just a way to just graph this, and you know, 2 equations, 2 unknowns. But man, you know, it'd be a lot of writing. You're going to have to throw it in your calculator anyway. Be kind of cool to do this one without a calculator though, so I'm going to do that before I go to bed. You know what I mean? If it didn't have a calculator, well, you know what I mean. Well, inverse tangent, I don't know if you'd be able to do that one. That one wouldn't come out good at all, would it? I'd have to look. There's a way to do that though. Alright, anyway. Cool, so I'm going to do this. I'm going to go 18 plus 9 cosine 60. Cool, and I'm going to go negative that. I'm going to store that as alpha m. Just picking letters. Okay, so now I'm pretty much good to go. Well, I could even do this. I could go negative 16 times 9 sine 60. And I'm going to store that as alpha r. Hell yeah. And then I'm going to go 16 times 9 cosine 60. Alright, I'm going to store that as alpha w. Cool. And, alright, so now I think I'm set. That's good enough. So in my calculator, I'm going to have this is my y equals. So I need to get everything over here. So I'm going to do a parentheses. I'm going to do a negative. This is my x term. Cosine beta. And now I'm going to need to get this term over. So I'm going to subtract it, alpha r, because this whole term is r. So I'm going to subtract r on that side. Parentheses, divide by alpha h. Hell yeah, and that's my y term. Now I'm going to come over here, I'm going to go parentheses negative. This is my x term, sine, in my calculator, sine beta. Cool. And then I'm going to subtract this w term. And booyah. And then I'm going to divide by alpha m. Alright, hell yeah. And our window on here, let's graph it up and see if this is the last one I was doing. I don't think so. So I'm going to go zoom fit and see if that will kind of choose some coordinates. Not really. Alright, let's see what we got. And then what are we doing? We're trying to get, yeah, this velocity is hella huge. So this is almost like 200. Yeah, I'm glad we did that. We thought it was like 144, maybe 136. Let's throw that in, 144. That's really cool. And then what do we think our radians was? We're going to go 0 to 10. And then hell yeah, so that should graph, and we should see where they cross. It's always good when doing these equations. What are you expecting? And so, yeah, near a speed of 144. No, the speed's way less. Oh, so it was. The speed was way less. When this is over here, it's still kind of going more vertical. So if this thing is going vertical, it's not jamming through that shaft. Hell yeah. So that's first, second, and then curve. So that's interesting. So we were off on our speed. We thought the speed was going to be 144 or 130 or 120. The speed is actually 94, and this gives us our radians of 4.57. So hell yeah. So we have a radians of 4.57 radians per second. Sorry just to scribble it out because I get exhausted from these. But we learned a lot, and hell yeah. You know what I mean? I think we did everything crispy except the actual problem. You know what I mean? We just kind of rushed through that. But no, we did. It was kind of interesting. So hell yeah. And we got two equations, two unknowns. What do you do at that point? The second you get two equations, two unknowns, you're like, well, like it's either right or it's wrong. And it's right in this case. So that was pretty sweet. But that's one juicy way to do two equations, two unknowns. Put them in your calculator. But I just know if I put these two equations in my calculator, they're going to go past there. That's why this calculator, I don't know. It's the generic standard, but it's not the gold standard. It's just the generic standard. But anyway, it's really difficult. The second your equations get passed and you have to scroll back and forth, really easy to make mistakes, and it's very difficult to catch those. Alright, so we did it, and we did it juicy. And this actually puts, that's our speed. And both are positive, so we chose the right directions, you know what I mean? This bar is rotating in the k-hat direction, 4.57 radians per second. And let's talk about that. You know, again, 6 radians is a full circle, so 4.5, well, hell yeah, that's about 3/4 of a circle, you know what I mean? So this thing is spinning 3/4 of a circle a second. Every second, what, is that thing going to whoop around? No, but that's the other thing about these problems. That's just for that instantaneous in time. We said when this bar was here that there is no rotation. No. If this bar is right there, there is no vertical speed of this through the shaft. There is almost pure rotation. That would be hella, actually. So let's finish with that because that would be fascinating. If this bar is here, so I'm just going to bring it down to there. This shaft is here, and I'm just going to rotate this bar up 30 degrees. If this shaft goes up 30, well, what do you think this angle does? It's about the same, you know what I mean? Again, if this goes 30, this goes about 10. If this is 30, this is about 10, and you still have a third. So even through this whole sweep, the angular speed of this is about a third of that. Is there any point where it actually gets... I mean, there's a point where the angular speed, you know, goes to 0. But yeah, the angular speed is going to be the highest when you're at this flat angle. 0 to 60 is where you're going to see the biggest angular speed. Once you're at a perpendicular, you're going to see hella velocity, but then not a lot of angular speed because it's just all linear. Hell yeah. Alright, I am thoroughly done with this one. But thanks for joining me. And I think we did pretty good. So this was crank AB, rotates with... I don't want to read it. Anyway, thanks, and booyah.